Hello YouTube and welcome back to Impl PERT. In the last video we were just starting to implement some of the functionality within our structs and traits. So we did our Impl struct PERT task trait. We added the ID, dependencies, duration, early and late start and finish times, and the relationships between the parents and children for those tasks to create our PERT graph. We implemented partial equals for the PERT task, and some convenience functions of creating a new PERT task is critical and slack. So those are the results that we might be interested in generating out of our PERT analysis. We also then introduced our implementation for PERT for a vec of t that implements try into PERT task, and we demonstrated how we just created a vec of PERT tasks using the try into PERT tasks function in the PERT trait, where we iterated through the vec of t and call try into PERT task. We will return append the task if it was successful in being converted into a PERT task, and it would append to the errors list if one of those tasks errored when being tried to be converted. And we would return either the tasks or the list of errors if more than one task fails. We also did the solve PERT, and that's where we got to at the end of the last video, which is how we start to build the graph. So the first thing we do is actually take the vec of t, turn it into a load of PERT tasks, and wrap around an RC new ref cell around that, so we get a vec of what we call PERT task strong refs, because it's a strong reference. RC is a strong reference to the PERT task, and then we build the parent edges and child edges. We need those to be strong tasks because we downgrade those to weak references within the parent and child variables, the vectors, within the PERT task itself. And you do that by having to have a strong reference that you then are able to downgrade. That gives us the ability to have references across all of the PERT tasks, and we can call upon those to get access to the parents and children as and when needed when we're coming to solve the PERT problem. So we did that. We built the parent edges, we built the child edges, and now we're on to the stage of solving for early and late times and then returning the result. I mean, we've been doing a lot of implementation here, and I really haven't seen where what the result might look like yet. So I think maybe the first thing I'll try is, rather than continue solving for the early and late times, we will just do a quick little test. We'll build a little quick test to show how we might. We'll build a couple of PERT tasks with one dependency between them, and just show you what the output looks like, so you can see what the vector effectively of this PERT task is, just to help maybe contextualize what is happening here. So to do so, we will go down to the bottom of the script and we will create a CFG test, mod test, and we will do a new test, and let's say fn test 2 tasks. And we'll just simply here, like I say, this is not a proper test as such, it's just a one for that we will just use to demonstrate what's happening behind the scenes. So PERT assert equals false true for now, so it will fail. It will also fail because we will try and do the solve PERT bit, and we are able to do so. It will say not implemented yet, but I'll get it to print out what the if I put in here, I'll print out here and the tasks, and I think I'll need to implement debug. Here we go, scroll up here for PERT task. So we just have to do derive and debug the task. Okay, so what we want to do is, let's create let a equals a PERT task new, and we'll call it a to string and an empty vec, so it's not depending on anything, and the duration is, let's say, about 10. That's a float. Let's create another one. B equals a PERT task new b.to string, and do another vec here. And actually, this is going to be a to string. So it's A's, B is going to depend on A, and the duration of this one is, say, 5. Okay, so we've got now 2 tasks. Oops, a space here. And we now want to create a vec with those 2. So let tasks equals vec, and we'll put in A and B. Okay, so because we could call these directly up, we could just make this an array that's saying now, because actually we've got a fixed defined tasks, so we could just use it as an array. I want to keep it as a vec because we've implemented vec for vec, so we'll see this in a minute. So we've got a vector of tasks of A and B, and if I then so call on tasks that solve this way is where I need to import the import PERT into our scope for our crate. I know it's unused at the moment, we're just going to about to use it. Solve PERT. Oops. Yeah. Input meet. Why does it not like that? Not satisfied. Because this is not a vec of T, so we can't necessarily, because that's a vec of PERT tasks. We can implement it try into in itself. What's the easiest way to articulate this? What we could do, rather than call solve on this, because we've got the tasks, what we can do to do this, we will need to, and this is just for demonstration, we will have to do Impl here we go, try in, so this is kind of going to be a nested bit, so we're going to have to do try into PERT task for PERT task, and then it's fn try into PERT task, and it's going to be okay PERT task self, and we're going to clone ourselves, so I'll need to implement clone. So the challenge what we're having here, is that, of course, an array of vector tasks, PERT tasks, do not implement try into PERT task. So all I'm going to do is that it's going to create another version of itself for this demonstration. So I need to implement clone to make a clone of itself. And I've implemented here try into PERT task. So I mean, this is effectively what you could amend a user would do, but for their own struct type. And it's also saying that we need to define the type error. So we can equal, and this is going to be infallible because it can't, like, if we've got a valid PERT task, then we can then clone ourselves, and we should be able to create our own PERT task. In effect, actually, what if we were going to, let's assume that this PERT task was a task, generic task in another library that they want to implement PERT task on. You could imagine then someone creating PERT. Maybe this is what saves us having to implement clone, but it's okay to keep clone. We could say let task equals PERT task new, and we would then take here self.id self.depths and self.duration. So in effect, we're doing the same there as making a clone, and we're going to return task. And these behind shared references, so we need to clone these in this case. And there we go. So now we've implemented trying to PERT task for PERT task. So it's a bit nested. Effectively, we're making a copy of ourselves. This then should, if we go down here, should fix our little error of that. We've got now a vec of PERT task. Let's do that. Just clearly define it. And what we should be able to do now is then solve. Let's say let tasks equal, or let's say PERT tasks equal tasks dot solve PERT, and a max iteration. Let's say over 1,000. Because we're not using it at the moment, and yeah, we're not using that, and we do not need mutable here. Okay, so now it does a bit nested, but hopefully it makes sense that we have created a vec of PERT tasks, but this could be any other struct as long as it implements try into PERT task. So then it adheres to this constraint that it's a vec of t. Try into PERT task also implements partial equal, which PERT task does. So those are all valid. Therefore, by including that into our scope, PERT task here, we get these functionality. We're awarded, as it were, this functionality of trying to PERT tasks and solve PERT. So now we can do solve PERT. I've done them just the assert equals false and true. So we should now, this will run solve PERT, and we'll get to the stage where it'll print out the tasks. It will then error because we have not, we've got they not yet implemented in there. Fingers crossed. If we've got this all right, I'll just exit that and do cargo test. And there we go. So we have failed, which is exactly what we expected because we have not yet implemented. So that's the to do macro there activating. But here's what we're interested in. I wanted to show you what we've produced. We've created those PERT tasks. We've then wrapped them in those ref cells, and here's their IDs, dependencies, durations, early start times, references. And then if you see into parents and children here, we've got children. There's a weak reference to something else. I mean, it hasn't printed out the full variable in here, but that is the weak reference to B. And then in B, we have the parents, and it has a weak references to A. So that's how we're creating that graph. And we have then the min maxes. These are all the default variables. That's why you get these large numbers here of the min max ranges that we default to when we create PERT task new. So that's what we have. What we've got to so far. We've been able to create PERT tasks and produce basically the vector is the project, as I said before, and within it, it's got the vector of tasks, all the tasks that are associated with that project. We associate themselves with one another using weak references. That will enable us to traverse them. So there's no separate edge set here because the edges are within the nodes themselves, as it were. So with that done, we can go back into here, and really like to today was focusing on solving for the early and late times. Now that we kind of know what, hopefully that's given you some idea of what the vector that contains. So again, what we want to do is create another set of functions that work across a slice of task refs. And in here, we're going to do our first one. So we're going to look at solving those. So delete that there, and we're looking at solving our early times. So we'll do fn solve early times here. And we're going to pass this a mutable tasks, and this may error So just like that, we're going to use PERT error. So we'll need to give it the type T because we're going to pass it that for being able to propagate the error type. And we are going to then put a question mark there because we'll propagate that error up. Now we'll see that in the the definition of this function is similar to build parent edges, where we'll do solve early times, and we have a T, which is then try into PERT task, so it has to implement this, and it's a reference of tasks as before. It's a mutable, has to be a mutable slice into a PERT task strong ref, and we have the max iter here. So this is where the max iter will come into, and we have defined it as a usize. So bring that back in here. So this is where we're going to call it, and we will use it. We might error on it if we find ourselves in an endless loop. What we will return back is going to be nothing, as okay. We've updated that task, so we've populated it with early start times, and we'll error on the PERT error. Of course, that PERT error has a T, which we're just going to pass it as the T.error. That's been passed down through the PERT function up above. Even though we're not really calling upon it in here, it won't be. I don't believe we'll have one of those errors appear. It's just the fact that we combine the errors into one single error enum here. We could, maybe have two types of error in the fullness of time, but for now, it's a single error type. So solve early tasks we need to pass the max iter in here. There we go, and that will use the. Oops. Yeah. And this one needs a double colon. Okay, and we will say okay just to delete that. Right, now we need to solve the early time. So what are the steps that we need to do? Well, the way that the process I've gone around processing these early times is that we need to start at the start a project, and it is then traversed down, and all our if the graph is well defined or well structured, then we should always end up at end of project, no matter which way we traverse. We should never loop back, and we should always end at the project. So what I ended up doing was to have a vecdeck. I'll call this the processing vecdeck. And these are the nodes that we want to process next as we go down or through this graph structure. And these are going to be strong reps. Okay, it's a vecdeck new. Okay, so it starts as empty. So what we need to do is find the first, starting tasks. It could be typically one in the so that was the start of project one in the Wikipedia example. You can have multiple start points. They could be. In this case, we look for that for those starting nodes. So they will be the nodes that have no parents, no dependencies on anything else. So we go for T in tasks dot iter, so iterating through them. Pardon me. So if t.borrow, so we're going to borrow it out of the ref cell, and we don't need to mutate it, so it's just a simple borrow. If the parent is empty, then we will then go processing dot push to the push to the back. And we're going to clone the reference. So if I just go over to T here and show you the definition there, it is the RC ref cell. So if you clone that, you'll get another RC ref cell out of that. So it's another strong reference to it. And we put it into our processing. One check we want to do here. If processing is empty, then we can return an error, and we need to define this error as like no starting tasks. So no starting tasks. So oops, I need to double click on there, and we need to define that up in our errors. So we'll just scroll up to errors here, and we'll do no starting tasks. Don't think I need that. There we go. So iterated through, identified where the parents are empty, so it must be a starting task. We have then pushed it back into the vec deck. So for those quickly, for a vec deck is slightly different to a vec, where you can push and pop from either the front or the back of the deck vector, rather than like a typical vector where you append, you push to the back. So you'll see where this comes in useful when we do a loop, as we loop through as if we're navigating this graph from our different nodes. And that's what we're going to do now, where we've got the starting task to process. We've got to go and start processing those and iterating, getting to the next task, updating the early start times for all those tasks. So we'll have an n of usize. Oops. We'll set that to 0, so that's going to be our iterator, just to keep track of how many iterations we do, and we'll check that with the max iter, just in case we end up in a loop. We could be a bit more intelligent and try and find any loops before we do this, but I've just got there using this max iter as a way of catching that. So while that's in task, and this is where we go through, we're using vecdeck, we go processing.pop front. So we're going to take the first one out of the list, not the last. And we're going to go, okay, let's have a look at this node. Let's look at this task, update the values. If it's got any children, we'll append those into the processing, because we're going to process those next, and then we're going to keep processing down the graph. So we're going to iterate, increment by 1. Then if n is greater than max iter, we can then return an error. To say PERT error max iter reached, and we can return max iter so we know what we hit. Okay, so we need to add another error there. Just if we've kept looping for so long, we may have never ever reached, we may have entered a loop, so we'll just return the error to the user. Maybe you want to adjust, it might be that we need to increase the max iter range, or that we are in that loop. Okay, so now that's just that check. Now we want to do actually the updating of those start times. So we need to do let meet parent equals task dot borrow. So we're going to call this is the parent node that we've just been given, which is just renaming it for convenience, and we're going to get a mutable borrow to it. We're going to see the early finish time. We're going to compute this for it. Will be the parent dot early start time plus parent duration. Okay, so even what the parent's early start time is currently, add the duration to that, and that will be the early finish times. And then we do parent dot early finish time equals that finish time. So we're just updating that within the parent. And then for any children that it has, spacebar's not working that well today. In parent dot children dot iter. So now we're going to loop for all the children of that parent, and we first want to upgrade our reference to them. So remember, we've got weak references to those children, so now we want to go I want to I'd say necessarily a real reference, a strong reference to that, then we were able to then borrow it. So now we've got that reference to the child for this period of time, for this bit before we drop it. If the parent early finish time is then greater than the child's dot with borrow, and then the early start time of the child. So as we progress, we may revisit some of the tasks again. So what we're doing is we're at this parent task. We're going to check its children. If my finish time is later than the early start time, well, I know that I need to then update that child with the early start time with my finish time, as I might be the latest one, the one that it has to depend on most. That's it. There may be another one that's got a finish time that's later than me, which then will update that child. And then, of course, we might need to have to then reprocess that child to put that into the processing list, and back around the loop it goes. And that's it, really. That's us going from, imagine the top of the graph in our video 1, going from the start of project, iterating down this tree, diverging where we need. And I said this is then iterating through those tasks and then populating that processing. So we're constantly processing the next set of tasks until a stage where we get to tasks that have no children. Therefore, nothing will be pushed to processing. Processing will empty, and therefore we have reached the end of the graph. So that will then complete. So that is then solving our early times. Then we get to the stage of solving the late times, which in essence is the same but the opposite. It is going to go from the end of project and work our way back up. So in much the way that solve early times is set out like this, we have solved late times, and it is the same kind of structure. Immutable tasks, we'll have then max iter, and we can solve that. So now we just need to define it. So maybe if I just yank that and copy that one out, and we can then do solve late times. And I need to, let's just put the, okay. Right, so now, and pretty much the same thing as again, we're going to create a vec-deck. We're going to populate that with the tasks with no children this time. We'll find the latest one with the latest finish time, so that would be the end of project. And then we're going to iterate back up to determine all the late finish times and start times for the other tasks. So let's start with that. So then that mute processing is then a vec deck of PERT task strong ref, and we'll just do vec deck new again. Missing a G. And then we want to do, okay, so let mute latest. And we're going to call that, it's an F32 and 0. So what we want to do is go iterate through and find the task with the latest finish time. Again, there's a couple of checks here maybe that we need to do, is that make sure that there is only one single finish node, which is actually not in place at the moment here. If we went through the tasks, let's assume that it was a graph that completed to a single node. We'll iterate through these tasks. Let t equal, then we t.borrow from the ref cell. We borrow out for this period of time. Let time, let's say, equals t.early finish time. So let's get the early finish time. If time is greater than latest, that must mean the task runs beyond the current the current winner, as it were. And we go latest legal time. That's going to find us the latest time. And then in that, we will then go for t in tasks again, dot iter to find, and it may be that actually we can keep something that I might have to update later actually, because this is probably 2 iterations where we can reduce this down into one single one. We could go to well, actually, why not? Let's do let's make this an option. So this is going against the actual implementation I have on crates.io, so I might update this later. We have this as t let's say last task is going to be an option. Task strong ref, and it's going to start as a none. So we haven't got one initially. Change that as mutable. But if we have time is greater than the latest time, then we will do we'll update the latest time, but also we'll do last task equals sum t.clone. We can't borrow, no, we can't. What we need to update here is put that as t, and this then trc, and then we can trc clone. So we're going to clone that. Fine. Yep, we haven't assigned it yet. It's okay. So now we need to. So we've got some task. So if we then go if let non equal last task, then we want to return an error. PERT error no last task. Okay, and then we just need to update our errors. No last task. So effectively what we then there is to say, well, where am I? On myself again. Here we go. So we're saying the latest, we feel it's got to be greater than 0. We don't have tasks that go, negative in time, in duration. So if we haven't found anything that's greater than 0, then we haven't found a task. Task is none. More or less, we should find a task. Now we've just copied that as the clone. We will then put that into then if there's we could do this as a match statement actually. Let's do that. Match match on last task, and if it's an error, if it's none, sorry, then we return. If it's okay, t, when we're processing, we'll push it to the push that to the back. So that's going to be our starting task to iterate back through. Oh, not okay, sum. Sorry. Yep. There we go. So we should receive a task. If none, we haven't found the last task. Should probably never happen. We should never get to this stage. But it's good to have that check in this case. Now we do let mute n is usize 0. So again, we're going to create this n that's going to increment every iteration, and we're going to check it against max iter. And then we're doing the same process. So we'll do let and we're going to call this some child. So as long as the processing queue pop from the front again returns us some tasks still to be processed, then we'll increment by 1. And if n is greater than max iter, then we will return an error, PERT error, max iter reached, return the max iter size, so the user knows what they put in. If it's all good, we're still able to iterate, and we'll go and get a child.borrow mutable. So we're going to update the child. In this case, I've called it delta, so I'm looking at the diff. Well, we could call it diff. So now we want to have the difference between the child late finish time minus the child duration of the child task. Duration, and we will then assign this to the child late start time. Okay, so it should feel very familiar and similar to the previous one. All we're doing is reversing the order in which we're processing this graph. And for parent in child parents iter. So now we're iterating through the parents of that child. We want to get access to the parents, so we need to upgrade that weak reference. Parent.upgrade .unwrap. And we unwrap here because, like I said, we should, by this stage, we know that they exist. Nowhere in the code, but these are all internal functions here and only called by solve parent. We know we've built all the parent edges and child edges, and we haven't dropped any. So the RC, that strong reference is going to be still around. So whilst, if let's say that strong reference had been dropped, yes, there would be a case where the parent doesn't no longer exist, and this would error. But it should never do that. It should unwrap. We could put an expect here actually to say, parent should still exist. So we're expecting that the parent should still exist. And then let mute p. Let's then actually mutably borrow that parent from the reference, from the RC. Sorry. And if p then dot late finish time. Oops. Equals child dot late start time, and then we will get the p dot late finish time equals the child's dot late start time, and then we put the parent into the queue to then check for its own parents and so on and so forth. So push that back, parents dot clone. Mutable. Oh yeah, need to add mute here. Okay, so hopefully that's just it's the same process but in reverse. So we're taking the child, borrowing it, looking at late finish time minus the duration to create the late start time. We're then going to go through the parents, check their late finish times. If they happen to be greater than the late start time, we need to know. We have to kind of push that project back, that task back there, and then update its finish time. Because we've updated that, anything above that task, as it were, will need to be updated. Might need to be updated. So therefore, we then clone that into the processing pile to be processed in the next iteration. And they all get propagated up. We'll iterate all the way through until we reach the start of project where we have no tasks with any parents, so the processing won't have any additional tasks to process, and it'll exit unless we reach the max iteration stage. And that is all the processing that we need to do to actually solve the solve PERT. That is us completing that, populating it with all the values we need. We can then return OK. Oh no, sorry, we don't want to return like, yeah, we want to return an OK, but we want to actually return the tasks, because then we want to do some post-processing on it and maybe get some insights onto the critical path. So we want to return, so we want to be able to take the tasks out of their strong references. So what we want to do is get the owned version back. So let's say we're done with having these RCs, having all the parents and child relationships. We can undo effectively all of that, because like I said, they're private variables just for the processing this data. We can now take that all back out and just return the vectored tasks to the user for further interrogation. So we get the tasks, we do into iter, and then we want to map, so go for each of those tasks, and what we want to do is then let RC, let T equal, I need to, so curly brackets first. We need to let T equals RC try and wrap T. We expect should only have one strong reference, strong RC, and that is the one that's in this vector. That's it. And all the other times, all the other like clones of that RC will have been dropped within that function. So the only one that's available or should be available is that strong RC in this spec. Then we can let mutable T equal T.into inner. And what we want to do is just clear, and this is just a bit more, not that like the users can never access these fields, but it's good that we might as well remove these weak references, because the strong reference that they relate to no longer exists as strong RC. So we just do clear on those parents and children, and we return the T, and we collect that all up. So basically we just take them out of the RC ref cell, and then we return that. So I believe it's reasonably memory efficient, because it's still using the existing vector PERT tasks. So all we were doing there effectively is wrapping an RC ref cell in there, and then we're unwrapping and taking those out again. So it's been the same, effectively same PERT task throughout the iterations. So that gets returned to owned and given back to the user. Right, so let's see what's the best way to process this. So we've got our PERT tasks there. Maybe good to, let's do this print line here. So we'll go back to our test, and we'll debug our initial tasks. We'll print line, just put some spacing, and we'll solve the PERT tasks, and we'll print line the result here so we can see what's going on. Oops. PERT tasks. So fingers crossed. I'll just print line tasks. Yeah, so we need to unwrap this. Infallible doesn't. Okay, yeah, I need to derive. I need to derive debug for this, of course. Debug. There we go. So just drive and debug for the error there. So that's what that error there was. And we should now, hopefully, just write that and quit out, and we can go to cargo test. Okay, so yes, we have failed on the left-right assertion because we've just done that's false and true, just so it'll get do the printouts. So if it all, if a test, a Rust test passes, it won't do any of the print line, any of the stood out. I'll just make it fail so we can see it for the demo purposes here. We start off with PERT task here with a duration of 10, start times are all in their default values, parents and children are empty vex, we don't put anything into those, and then as we go through, we have still printed out the same. Why is that? No, yeah, so yeah, absolutely. So this is great. Yep. So I'm just trying to read it myself. So yes, the duration of here, the early start time and finish time is 0 and 10. So we've updated that. So finish time is 10, not minus 3.4 e to the 38. We have our late start time, which still hasn't been hasn't updated. So we need to look at that, and late finish time. But then in the PERT task of B, we have its dependencies of A, it's got its duration of 5, its early start time is 10, which is good because it's getting that from there. Its early finish time is 15. Again, the late finish times are not up to date, so we'll have to look into that. Did I actually add the function into... Oh, we do have solve late, yeah, right, so for some reason... is not doing, so maybe how I've done this is not necessarily the right way. Let's have a look. Print line last task. Let's put that above there so we can see what it looks like. Problem of going off script. Okay, so last task. If time equals early finish time, if the time is latest, yeah, so we update the latest time, we clone the last task in. Right, okay, let's have a look at see what that's going to give us when we do cargo test. Yep, so it does pick out B as the last task, and it's got its weak reference to A. The late finish time. Do I not start at finish time? Right. Okay, so let's have a look at. Go back down to late finish times. Let's borrow. Right. My bad. There we go. I think I know where the error is then. Okay, so just double check here. Right, so the late finish time. Aha, yes. So before I do this, of course, I need to access that late task. So I will do it here. So this was me going off script and forgetting to put a bit of functionality in. Because we've got this last task, the bit that we need to update processing is here we're using late finish time, but we actually haven't updated the late finish time to match the early finish time of the task. We just need to do task t.borrow mats dot late finish time will equal latest, because we've got it up above here. We can use that variable, and then we'll push it back into the processing pile. So then we're not starting at the maximum value that it can be. So hopefully, if we write that up and quit, now do cargo test, we should get some there we get some times that are a bit more understandable, a bit more obvious that they should be the right way. So we start off with our here you go, A and B tasks with our very high and very small values or minus values, the min and maxes. We've got our dependencies and the durations. We then have our reference there, and like as you can see, when we did our reference, we have our late finish time is very high there because we actually hadn't updated it with our early finish time, so it should be 15. We've just added that change in, and then when we've completed it, we have now got A and B, and the late finish time is 15. It's 5 plus 10, and it's propagated it back. So we've got the late finish time here of 10 for A. And of course, because they're only the two, they are on the critical path, they're the dependencies on there. So we have now completed, we've now resolved that PERT, the two-node PERT graph that we have. I think the last thing I want to show in this demo here is how we can do some analytics on there. So we're not even that far off. What we can first of all do, that's it, if we can just tidy these up. Because we've got these PERT tasks, we can then do for, let's say, P in. I'm going to have to look into my spacebar. For P in PERT tasks, we can print line, let's say, let's say a task, task name is critical. Is critical the answer. So we expect these to be both critical, so we can then put in p.id, but also we implemented the is critical function on there, so we can call that to actually do that analysis for us. The other thing we can do, and I think we've got it as still a to do, is identify the project duration. Okay, so do that on the self.PERT task will be to for p in p.iter sorry, for p in.self, and let's say latest equals 0. And we can do, let's say, let's say let if latest is less than p dot late finish time or early finish time, it doesn't really matter. That's why not it, because they should be the equivalent for the last one, and we will then update latest to equal early finish time, and we'll return the latest. So that should give us basically go through the graph. This is saying, or iterate through the vector PERT tasks with that graph and pull out the largest latest early finish time, which will be the final project time. So we can then say print line, project duration, and do p dot PERT tasks dot project duration. So now that because we've got a vec of t, so I just need to, as a .iter, now that we've got a PERT task which is a vec of t, that we've already implemented this post-processing capability, and it's already done this automatically. Sorry, that's what happens with the with our IDEs these days. We've got a crate, and it's imported the post-processing trait. Therefore, we get given these on a vec of PERT task. That's because of the implementation of that trait. Therefore, we will get the ability to do project duration here. So now we have our ability to imagine there is some way, for us we're just using PERT task, but in in somebody's other library where they've got tasks that have a different structure and data, they have implemented a way of doing try into task, PERT task. They would have created their vector of tasks, then they would be able to call solve PERT on it, because it would then convert them into PERT tasks, and then we will run the solver. We get that vector of PERT tasks back, which then we can then query the tasks for information, and we can query the vec as well to get project durations, and that's from our post-processing trait. So if I just quit out there and do a cargo test, what we can see is here's some of the analytics that we can get. So task A, is it critical? Yes, it's true, and the same with B, and the project duration is 15. So there is our, that's effectively how the crate works, is that you Impl try to PERT task, we're able to do that analysis and use the implementation to solve the PERT problem, and then we can then get some interesting statistics out of that. And the whole library also has the Monte Carlo processing as well. So if you wanted to run multiple events, we can do that. I think that's where we want to finish today. Last, only one thing that I think we could cover is there's a generic task Impl in the PERT the crate itself, which enables you to select different types of durations based on different distributions. So we can that's more of a demonstration of how you could use this for doing that kind of Monte Carlo simulation. So we might do that in the. So thank you very much for watching. Hope it was useful, and I'll see you in the next one. Bye.